So our next speaker is Laurent Bindschaedler, who will be talking about chaos, scale-out graph processing.
All right, thanks. Good morning, everyone. So it is my pleasure to present to you today the culmination of about 2 years' worth of hard work. This is joint work with Amitabha, Jasmina Malicevic, and our professor at EPFL, Willy Zwaenepoel. And this talk is about graphs. So graphs are everywhere. Graphs are very useful in a variety of domains, from social networks to internet companies, brain, road networks, national security, and whatnot. And the one thing is that we can say about all these graphs is that the size is growing. You may ask, how big are we talking? Well, Facebook gives us an order of magnitude. Facebook says we should design systems to process graphs in the order of 1 trillion edges. And this is actually what they did with Giraffe. Well, we built a system that can handle 8 trillion edges on 32 machines. This system is called Chaos, and Chaos is a system that uses very few machines, typically one rack, 32 machines, and secondary storage. So we don't do in-memory computation like these guys. This is what it used to take to process large graphs, basically throwing resources at the problem. We don't do that in Chaos. Of course, there's a trade-off. We trade speed for cost. So if you want to go fast, you will have to run from memory. We don't do that. We run from disk. We're slower, but we are more cost-effective if you want. So this is the recipe for Chaos. Chaos basically contains 4 main ingredients. These ingredients work in synergy: Edge-centric scatter-gather, streaming partitions, chaos or flat storage, and work stealing. We didn't invent these new principles. None of these are really new. The idea is that we use all of them in synergy to do graph processing, and this is actually what makes Chaos so effective. Permeating the entire design is the use of randomization, and actually this use is the reason why we call the system Chaos. So what are the problems when you want to do large graphs, when you want to process graphs in general? Well, there are quite a few, but the main one, at least the one that matters for us, is the fact that graph algorithms produce random accesses. And, well, it's not so bad if you run from RAM, but as soon as you start going to SSD or disks, it gets much worse. In this talk, we're going to be answering the question of how we can achieve sequential access to secondary storage in a scale-out manner. We didn't start from nothing. We actually started from Xstream. This is a system that was presented at SOSP 2 years ago. Xstream is an edge-centric graph processing system based on streaming partitions. In a nutshell, the idea of Xstream is that you place the vertices in main memory, so you have random access there. You place the edges in secondary storage for sequential access, and then you reorganize the computation to stream the edges from disk. Thereby, you can unlock the full bandwidth of these devices. So this is the computation model. It's called edge-centric scatter-gather. The idea is you store the state for your computation in vertices, and then you have really 2 operations that you run back-to-back iteratively until some convergence criterion. So this is a scatter, the first operation. It's very simple. You go through all outgoing edges, so you actually stream through all your edges in any order, and you apply a user-defined function to the vertex value to produce an update, which you then propagate along the edge, so from source to target. In the gather, what you do is you go through all edges, through all incoming edges, through all updates, if you want, and you apply another user-defined function to the vertex value and the update that was just sent to produce a new vertex value. So you update the vertex value of the target. I just want to make one thing clear, and this will come back later in the talk. So these operations are order oblivious. It doesn't matter in which order you go through the edges. You just have to go through all of them, but there is no concept of ordering these. Okay, they're order oblivious. So how does this look like on a single machine? Well, so on the left, you have a graph, vertices and edges, and on the right we have a machine, some compute and some storage. Of course, there's no guarantee that the vertices will fit in RAM of the single machine. So what we have to do is split the vertices in what we call streaming partitions, and these streaming partitions are such that the vertices fit in RAM on the single machine. To these vertices, we associate all outgoing edges, so all edges whose source originates in the vertex set. And then how we execute this? Well, we simply go through them one by one. So we load the first vertex set in main memory, stream through the edges on disk, do the same for the second partition, and so on and so on. Of course, here I'm just describing the first part of the scatter, right? So after this, I will produce updates, which will be appended to disk, again, writing sequentially. And then in the gather phase, what we'll do is read in from the edges, from the updates, in a similar manner as we do with the edges. So always sequential access to disk, random access, and memory. Well, but I said we were going to scale out. Okay, so we scale out, we have multiple machines, and now this is chaos. The question is, of course, how do we distribute the graph among all these machines? Okay, and here we rely on the fact that these operations, the computation model, is order oblivious. That means the streaming partitions are independent, and that means we can just assign an equal number of these to each machine, which is exactly what we do. So each machine gets assigned one streaming partition, puts the vertices in RAM, and then of course the question is, what do we do with the edge lists now? One thing we could do, and this is the simplest thing we could do, is to place the edges on the disk of the machine to which the partition is associated. Well, there's just one problem with that. These edge lists are very different, potentially because of the parallel degree nature of graphs, typically real-world graphs. We could have a lot of I/O imbalance, and there's even no guarantee that these would just fit on disk on a single machine. So we don't do that. This is a false start. Instead, what we do is we rely on the fact that we're talking about secondary storage and a small cluster. That means the bandwidth to a remote disk is the same as the bandwidth to a local disk, provided that the network is able to sustain this bandwidth. That means actually we don't need to worry about locality, and we can simply stripe the data to achieve I/O balance. So this is what we do. We're going to stripe the edges. The first machine still gets the first partition, but we stripe all the edges on the disks of all machines. Same thing for the second machine. Notice that we keep all disks equally used, and so on until the last one. Okay, so now we have a good distribution of these edges through all the disks in the system. Now let's describe the computation. So to do this, I will focus just on the one machine. Of course, all machines do the same thing. And the question is now, we're doing a scatter, so we need to bring in some edges from disk, combine this with the vertices, and produce an update. Of course, the question now becomes, well, which stripe do we read? And we rely on the fact, again, that the order of the operations that we're talking about does not matter. That means we can just pick any stripe. Okay, so not just the streaming partitions are independent, but also all the edges and therefore all stripes. That means what we do is we just contact the machine at random, ask it for a stripe, which it reads, sends us back, and we can then proceed with the second part of the scatter. Of course, we just need here to make sure that stripe has not already been read. We place the responsibility to do that with the storage. But in fact, for performance reasons, what we do is we read multiple stripes at the same time. So we have multiple outgoing requests to multiple disks in the system. And the idea is to maintain high hard disk utilization. And there are more details for this in the paper. So I hope by now that I've convinced you that chaos can achieve I/O balance through this technique, which is very similar to flat storage. There's another problem, of course, is notice that while all edges are equally distributed on disks, some machines might still have more work than others. For example, in this case, the third machine only has 3 stripes to process. The first machine has, I think, 7, so a lot more. This is, of course, a computation and balance problem. So what happens when the third machine is done? Well, it has to wait for the first machine to be done. Okay, that's not good. So how do we solve this? Well, we rely on the fact that, again, these stripes are independent, which means that any machine can process them, and we can simply use the tried and true technique of work stealing to achieve computation balance. So how does this work? Well, assume a machine is done with its partition. It's going to randomly select another machine and asks it if it needs any help. The machine can say yes, in which case you proceed with the work stealing, or it can say no. And the reason for it to say no is because it estimates that the overhead of doing this work stealing is too high, and it's better to actually go and contact another machine. There's a heuristic that we described in the paper, but in a nutshell, the idea is that you estimate this overhead, and if it's too high, you say no. Okay, so as soon as the machine has said yes, so assume the machine said yes, the third machine in this case has to copy the vertex state for the first partition, so from the first machine. And of course, now it needs to also proceed with the scatter, so it needs to also do some useful work. But there's one thing that we need to be careful about here. I just said that multiple machines are going to work on the same streaming partition. That means multiple machines will access the edges or the updates simultaneously, which actually might mean that we might have a synchronization problem. Okay? Well, this is actually described here. So which edge stripe do we read next? And well, actually, there's no problem, because for the scatter and the gather operations, the order does not matter, again. That means there's no need to explicitly divide the work between these machines, and multiple machines can simply just work on the same partition simultaneously. So in this case, the third machine will bring in some edges, so we'll contact the machine at random and read those edges with which it will then produce some updates. Here, we also need to make sure that we don't read a stripe that has already been read. Okay? Remember that the first machine at the same time is also reading from the same stripes. We place the responsibility of ensuring that this doesn't happen with the storage engine in chaos. There's actually one price we have to pay for work stealing, is that multiple machines are going to work on the same partition. That means multiple machines are going to have copies of the vertex state. If we do a scatter, that's not so much a problem because you're just reading that and then producing updates. But in the gather phase, what you do is you actually modify this state. So that means multiple machines are going to have partial vertex states, and somehow they need to be reconciled to have the final vertex state. And what we do here is we ask the user to provide a third function, which we call apply, that takes care of doing that. If you're familiar with Powergraph, this is very similar to their gas model. So I hope by now that I've also convinced you that chaos can achieve compute balance through work stealing, and that I've actually given you a good idea for how these 4 principles, or these 4 design principles, interact together in synergy to build chaos. I've also given you an idea of where randomization comes in, especially with respect to the storage and the work stealing. So I want to talk a little bit about some related work. So the common wisdom in graph processing has been to partition to achieve locality and load balance. This is expensive. This is pre-processing. It's very expensive, and we actually dubbed this approach order. There are various ways you can do that. You can have edge cuts, you can have vertex cuts, some sort of sorting and sharding, and my favorite is actually the Hilbert curve approach, where you flatten the graph and then you make it very easy to split. In chaos, we completely depart from this, so we don't do any static partitioning. We don't worry about locality because we do flat storage, and we don't worry about achieving load balance through a pre-processing step, and instead we achieve this at runtime. So the idea is we have very low pre-processing, and we just want to start going with the computation right away, pretty much as fast as possible. So let's look at some results. Well, to produce these results, we have used 32 machines, typically one rack. These machines have some RAM, some storage in the form of SSDs and magnetic disks, and they're connected through a full bisection bandwidth switch. To evaluate the system, we use the RMAT graph generator, which makes it very convenient for us to get graphs of appropriate sizes, on demand. And the results that I'm going to report are the wall clock times. That includes pre-processing, so the time from the row edges on disk to the final vertex state. This is an overview of the algorithms that we implemented in Chaos. There are quite a few. You can do a lot of things. You can do traversal, filtering, SPMVs, mining, ML, statistics, and so on. And in the evaluation, we're going to focus on 10 algorithms, a subset of all of these, which we feel is relevant. Now, most of the results that I will show you next are normalized. But I want to show you actually the absolute runtimes to give you a feel that Chaos is in the right ballpark. And to do this, I'm going to compare the runtime with various out-of-core systems, both single machine or multiple machines. And you can see that Chaos, for example, runs on 32 machines, BFS on an RMAT 27 graph in 35 seconds. Of course, this is faster than the single machine cases. And this is actually faster than Apache Giraffe, with the important thing that Giraffe is running out of core here. So Giraffe is not particularly designed to run out of core. It has an out-of-core extension. Here we made it run out of core, which is why it's slower. So let's look at some of these results. And the first experiment that we're going to look at is the weak scaling. So weak scaling experiment, we start with one machine, a given input size, and then at every step, we actually double the input size. So we double the number of edges and vertices, and we double also the number of machines. That means the result is actually the runtime relative to the one machine case. It's, if you want to slow down, of processing a larger graph on more machines compared to the one machine. So these are the results. Left to right, all 10 algorithms. Again, left to right, each bar corresponds to a different number of machines, so 1, 2, 4, 8, and so on until 32. On the y-axis, you have the normalized runtime. The ideal situation is when this is just 1, so that's no slowdown. In practice, of course, the lower this value is, the better. We don't really get to 1 exactly. And you can see that on average, Chaos achieves 1.61x slowdown to process a graph that is 32 times bigger on 32 machines compared to the one machine case. So this is pretty good. And we actually have a worst case minimum cost spanning tree 229 and a best case conductance, which is a little faster than 1. Let's look at a second experiment. So this is a strong scaling experiment. This time we fix the input size and we double the number of machines. So we start with one machine and we double each time. The result is your speed up relative to the one machine case. And so here, again, these are speed up curves. So on the x-axis, you have an increasing number of machines, 1, 2, 4, 8 until 32. The y-axis this time is a speed up. Of course, the higher that is, the better. And you can see that each algorithm corresponds to one curve here. On average, we have 13x speed up. So this is also pretty good. And I want to give you an idea for why it scales well. To do this, I've plotted the aggregate bandwidth with respect to the number of machines. So I've done this for all 10 algorithms, and you can clearly see, so the black lines are the maximum achievable by the combined disks, and you can clearly see that Chaos achieves runs constantly at near maximum I/O bandwidth. But of course, it doesn't scale perfectly, right? You saw that it's 1.61x slowdown. Why is that? Well, in a nutshell, the idea is that the work stealing that we use introduces overhead, and this overhead is algorithm and input dependent. This is actually why the algorithms that you saw in the weak scaling experiments had different runtimes. You can also ask what happens if we have no work stealing, right? So is work stealing really necessary? And here I've plotted for all 32 machines on the run of BFS the runtimes. And this is where no machine is allowed to steal from any other machine. So each machine works on its own assigned partition, and that's it. And you can, of course, see that there is a significant imbalance, and we would want to somehow flatten all of this. And actually, this is what we do with work stealing. So you can see now that all the machines pretty much finish at the same time, and all of these bars that were above the black line before kind of all spread out, and the load is distributed on all machines. But I've said that chaos was not so much about runtime, it was not so much about performance, it's mostly about capacity. And so here I want to show some capacity results with graphs in the order of 1 trillion edges. So we start with 1 trillion edges, we double that up to 8 trillion edges. That's the maximum we can fit on our 32 machines with 6 terabytes, two 6 terabytes HDDs, and I plot the runtime in hours. And you can see that the first bar corresponds to the 1 trillion edge. That's an input of 16 terabytes. To process the graph, we have to actually do I/O in the range of 200 terabytes, and it takes about 9 hours to do so. On the opposite end, we have the 8 trillion edge graph. That's an input of 128 terabytes. And to process this graph, we actually have to do I/O in the order of 1.75 petabytes. We do this in 104 hours, which is a little over 4 days. I want to point out that there are a lot of additional results in the paper. There's a thorough bottleneck analysis, an evaluation of the features, comparison, a more detailed comparison to other systems. So please read the paper if you have questions about these things. Finally, I want to show something a little cool. So some of you might be familiar with this graph 500 benchmark. This is a ranking of almost 200 contenders, mostly HPCs. And here we sort the benchmark by capacity, so by size. Of course, the benchmark is also sorted by execution speed. Here we sort by size. And the question would be, well, so this is the top 10. Where do you think chaos would fit? Well, we haven't actually submitted the results yet. We'll do it soon. But we would come in at a nice 5th place using only 32 machines to process 8 trillion edges. I want to make again very clear that we are not claiming that we run as fast as those machines. It takes us 4 days to run this input. Typically, these machines do it in a matter of minutes or at most an hour. I just want to make it explicit that here we are using only 32 nodes, which is far, far fewer than everybody else in this ranking, even not in the top 10. So by now, I hope that I've given you a good idea for how chaos works, how the 4 key design principles interact together, and how randomization ties everything together. I've presented chaos. Chaos is a system to process large graphs on small clusters of machines. Chaos uses secondary storage, not main memory. It scales linearly with the available storage, both in performance and capacity. And chaos actually breaks the terascale barrier on a small cluster of machines by processing an 8 trillion edge graph on only 32 machines. One final announcement. So we are making the code for chaos available online on GitHub. This will be up sometime this week or next week. Please fork us and help us make chaos even better. Thank you.
Shall we? Phil Bernstein, Microsoft Research. The applications you're describing are basically bulk processing of an entire graph, algorithms over the whole graph. There are two other scenarios for which people build graph systems. One is knowledge bases, where they're basically doing traversals and short queries, often with sub-second response time, for example, for web search. Clearly, you're not trying to address that.
We're not doing that, no.
But
not with this work.
The third scenario is to run graph queries, things like Sparkle or some XPath-like language over the graph. Have you considered whether this is a good storage format for those sorts of graph processing algorithms?
We haven't particularly considered it. I guess we should look at this, yes. So there's actually some work going on in the lab right now with respect to some of these things. For example, you mentioned point queries. There is actually people thinking about this in the lab now. We're also thinking about what happens if your graph changes over time and you need to do a differential compute. But we're not doing that now, no.
Okay, thank you.
Hi, this is Aaron Lee from Uber Technologies. Great work. I just feel like, one quick question is that it seems like you do a lot of disk I/O, right? So in a shared data center, there are actually a lot of other workloads. So this may create bottleneck for the disk I/O. I'm trying to see, do you have any technique to make it more disk I/O friendly so that other workloads are not seriously impacted?
So the question is, what happens if the cluster is shared?
Yeah.
Pretty much. We actually the thing with Chaos is that we run at maximum bandwidth of the disk. Of course, this will impact other workloads. Actually, this impacts the workload of other people in our group. But we don't try to we could probably look into that, but we haven't looked at it. No, we don't do that.
Right. Can you actually monitor the disk pressure and then back off?
We do. We monitor the disk pressure. Yes.
Okay. Thanks.
That was the question.
Vasily Tarasov, IBM Research. I'm just curious regarding the I/O balancing, if you considered using or you are using a parallel file system that would automatically stripe the data across all of the disks that are available in the cluster?
We haven't actually. So the main idea is that we started pretty much from scratch and we designed our own I/O system. The idea really is that we want to avoid having any metadata. So there's actually no metadata maintained. Everything is handled through randomization. We didn't actually consider this approach at all.
Right. So I think it makes sense to consider it because that's exactly what parallel file systems do. They stripe the data across many disks, and the amount of metadata that would be, if your files are large, if your chunks are large, it probably won't matter that much.
Fair enough.
Thank you.
We'll definitely take that into account, yes.
Malte Schwarzkopf, Cambridge and MIT. So nice work. I have a very short question, which is, what is the bottleneck in the 8 trillion edge case?
In the 8 trillion edge
when you
case,
take 104 hours, what resource is the one that is bottlenecking the computation?
The bottleneck is the disk.
Disk.
Yes.
Okay. So with the 1.75 petabyte aggregate I/O figure that you quoted,
That's
if I do a back of the envelope calculation, that comes out as 150 megabytes per second per node, which is presumably the disk throughput, right? You're using magnetic disks, right?
Yes.
Okay, so have you considered approaches like what FlashGraph in ATC this year is doing and replace, put more flash storage into one machine? Because they show they can store 1 trillion edge graph in a single machine in Flash, and presumably your disk throughput would be much higher in that case.
So the question is, have we considered that?
Have you considered using Flash instead of magnetic disks? What would be the impact on performance?
So we already do use SSDs for example, the weak scaling results. We didn't consider faster stuff such as NVM, but I would say as long as your network overall can sustain the aggregate bandwidth of all disks, we will run at full disk bandwidth.
All right, cheers.
Eddie Kohler, Harvard. This is not exactly a technical question. I followed Frank McSherry on Twitter, and several months ago, he and one of your co-authors
Yes.
got into a rather hilarious trash-talking battle, which I can recommend for everybody. There was threats of mustaches being shaved or maybe grafted onto people. It was strange. I guess my question for you is, this was fun to watch from the outside. Was it fun to be on the inside of it? Did you find it motivating? Do you think we should do this more often?
Actually, personally, I found it really fun. Of course, I was actually I was actually the guy running the experiments that Amitabha used in his blog posts. That was a bit more work. I mean, I had some other stuff to do on the side, but no, I think that was a fun moment, and it's all in good fun, and you know.
Thank you.